Hi, welcome back to lecture 26 of MA 221, and today we'll be discussing about calculus of parametric curves. So this lecture will be pretty similar to one of the previous lecture where we have discussed about arc length, area under a curve, and surface area, and etc. So we already derived the expressions for those topics when we have equation involving x and y, like the Cartesian coordinate. Now we'll try to use those formulas to get expressions for parametric curves. Okay, so something like this. Okay, so the first topic is area under curve. So the setting is pretty similar. We have a curve uh, given with this parametric equation, x equal to ft and y is equal to gt. So this parametric equation is given by this blue curve. So now, so um, so the setting is pretty same. So say we want to like divide the. So first of all, our interest is to find this area, this whole area. But to do that, obviously we need to do some integration. For that, we will subdivide this into this small pieces like this. If we concentrate on this small slice, then by the previous discussion on area under curve for like xy equation, we see that this is the expression for area under curve y dx, and the range for integration will be from alpha to beta. But here we know that our y is same as gt, right? So let's write that down. And now what is dx? So I know that x is ft, right? So my dx will be just, so let me just write it properly. So if I substitute my x as ft, then dx will be f prime d dt, and y is given as g of t. So if I substitute all of that, I'll get gt f prime t dt, right? And now the integration will be on t, so therefore the range of t was from a to b, so that will be my limit. Okay, as simple as that. Now one quick note is we need dx over dt to be bigger or equal to 0 on the interval ab, or we'll need to change the sign of integral to get a positive area. Okay, so in our physical world, areas are like always positive, so therefore we have to make sure that we do not encounter any negative sign as the result of area under curve. And for to ensure that, we need to have dx over dt to be bigger or equal to 0. Okay, and as usual, our y should be bigger or equal to 0 to get a positive area. We will see one example to understand this note fully, but that will come later. So the first example is asking you to find the area of the area of one cycle of the cycloid, this. So we have seen what is a cycloid in previous lecture. So if you remember, that cycloid looks like this. Say this is at t equal to 0, and this point is when t is 2 pi. So this is one full circle. This is one full circle. Okay. So we are interested to find the area under this. this area we want to evaluate. So using the formula, I'll get this. Y dx is the formula. Now, what is y? Y is given as 1 minus cosine t. And if I take the derivative of the expression x with respect to t, then I'll get 1 minus cosine t dt. Okay. And t is varying from 0 to 2 pi as well. Let me write that down as y is 1 minus cosine t given. Sorry. And dx, if I do the derivative, then I'll get dx to be 1 minus cosine t dt as well. Okay, cool. So therefore, this expression becomes 0 to 2 pi 1 minus cosine t square dt. Okay, so I can write the square as 1 minus 2 cosine t plus cosine square t dt, 0 to 2 pi. And now we need to do the integration. So the first two terms are like easy. For the third term, we need to use the reduction formula, right? I've already seen how to handle this type of integrations. So using reduction formula, for integration cosine square t dt, we will get this in these two terms. So, and t is varying from 0 to 2 pi. Okay, and if I evaluate it, then at the end I'll get this. So 3 pi will be my answer. Okay, cool. For the next problem, we have to find the area under this parametric equation. So again, the same formula, y dx. Then as like y is given as 2 cosine t, and as x is cosine t, so dx would be minus sine t dt. If I put that in this expression, then I'll get 2 cosine t times minus sine t dt, right? And the limit will be from 0 to pi over 2. Okay, cool. So this is nothing but minus 2 sine t cosine t dt. Now again, use substitution. Take u to be cosine t, then du will be minus sine t dt. So this will be minus plus 2 u du, right? Which is nothing but u square. And then I can again transfer from u to t. So as u is cosine t, so it will be cosine square, cosine square t from 0 to pi over 2, right? So it'll be 0 minus 1 square, which is minus 1. So we are getting a negative number as area, which is a little bit absurd, right? So if I try to sketch the graph, then what I'll get. So see, my y was 2 cosine t and x was cosine t. So therefore, I can easily see that y is same as 2x, right? This is the, this is the equation involving x and y only. So if I try to draw that graph, then I'll get this y is equal to 2x. It's this, and then this is the area I'm interested in, and this area is basically should be 1, right? But we are getting negative 1, so where is the discrepancy? The reason is, so if I try to draw using the parametric equation, then though I'll get the same sort of graph, but at t equal to pi over 2, I'll be my particle will be here, and at t equal to 0, my particle will be at there. So therefore, my direction is this. So, you know, I can see that so if I come from this side to this side, so x is decreasing, right? But then if I follow this path, then along this path, when x is decreasing, t is increasing, right? Because t is going from t equal to 0 to t equal to pi over 2 at origin. So therefore, we can see that when x decreases, t increases, right? In other words, when dx is positive, rather, when dt is positive, then dx is negative, right? If I take small nudge around along with the t-axis, then I'll get negative nudge in terms of x. Okay, so but what is my expression for dx? Expression for dx was this. So minus sine t dt, right? So this is negative because my dt is bigger than 0. So this is bigger than 0, and sine t is also bigger than 0 when I am in between 0 to pi over 2. In this range, sine t is also positive. So therefore, both of this is positive and there is a negative sign in front. So therefore, dx is less than 0. So that is what the problem is. Because dt is bigger than 0, to get the positive area, I have to make sure that dx is also increasing. So therefore, I have to take the modulus of dx, and then I'll get sine t dt without the negative sign. And then if I take y modulus dx there, then I'll get 0 to pi over 2 and then 2 cosine t sine t, just by the previous process, just that this time the negative will be missing because this negative has become positive now, as I have choose modulus of dx instead of only dx. So, and this integration will be positive 1. Okay, so now you can see that this area and this area is same, right? Because if I only consider in terms of x and y, then x is like x is increasing, right? I'm taking the increasing nudge of x. So therefore, to make sure that in the parametric formula, my x is also increasing, I have chosen the modulus for dx to get the positive area. Okay, this is a little bit subtle, but I hope that you got the idea. The next example is you have to find the area bounded by this parametric curve and these two lines. So if I draw the parametric curve, then it will be like this. This is the parametric curve, and this is x equal to 1, and this is y equal to 1. Okay, so I have to find this area, this area under these three curves. Okay, so again, this area will be y top minus y bottom, right? Where this is y bottom and this is y top, right? Integration of this dx, right? I know that y bottom is just 1, so therefore it will be y top minus 1 integration dx. Now what is y top? This is this formula, right? So it'll be e to the t minus 1, and then dx, using this dx will be just cosine t dt, right? And then t is varying from 0 to pi over 2 given in the problem. And that's it. Then you have to do the integration by parts. So I'll not complete this, but yeah, this is sort of an exercise to look at. You can complete the integration by parts and get the final answer. Okay, this should continue. Okay, so the next topic is arc length of a parametric curve. Yeah, so this time also the setting is pretty same. Here also we have got a curve given by this parametric equation. and t is varying from a to b. Now, if we consider small little portion of the curve and name it ds, and corresponding points on the x-axis is dx, then you can recall that the the this ds in terms of x and y will be 1 plus dy over dx square dx. This formula is again coming from the previous lecture where we have calculated the arc length for equation involving x and y only. No t was there, okay, for equation having x and y. Okay, or the other formula was just when the role of x and y gets reversed, and arc length was given by L, which is just ds, integration ds. So to get the expression for parametric arc, the arc length for parametric curves, we have something like this. For parametric equations, we know that ds square is dx square plus dy square. How? Because say this is the curve, this is the parametric curve, and say this is a small little portion of the curve, and then this will be dx, this will be dy, this is a 90-degree angle. So by Pythagoras theorem, I can write this ds square is same as dx square plus dy square. And now I can rewrite this as dx over dt times dt square plus dy over dt times dt square, right? This should be fine. And then this is nothing but dx over dt square plus times dt square plus dy over dt square dt square. So this is, in other words, dx over dt square plus dy over dt square, and there is one more dt square at the very end. And now if I take the square root, then ds will be just dx over dt square plus dy over dt square dt, right? So my arc length expression for parametric curves will be just a to b ds, okay, where a and b were the range for t. And if I rewrite it, it'll be a to b square root of dx over dt square plus dy over dt square dt. Okay, cool. Now focus on the following example. So this example is basically asking you to find the circumference of a circle of radius r. So say this is the circle of radius r, and say this angle is t. Then by plane trigonometry, this length will be, so say this is the point I'm interested in. So this length will be just r cosine t. This is following from trigonometry, and this blue length will be I don't know, this will be just r sine t, right? So therefore any arbitrary point on the circle will look like this. X is r cosine t and y is r sine t. So basically I just calculated the parametric form of this parametric equation of this circle, and there t should be varying from 0 to 2 pi. Okay, fine. And now we can use the formula that we derived, which is dx over dt square plus dy over dt square dt. Okay, now this is nothing but, so dx over dt will be minus r sine t square, and dy over dt will be r cosine t square, and there will be dt more. If I again recalculate this, I'll be having sine square t plus cosine square t. Again, this is a famous identity of trigonometry. Sine squared theta plus cosine squared theta is 1. So therefore, I'll be left with r squared dt. and square root of r squared will be just r dt. Now my arc length will be just integration ds. So ds is ds is just r dt, and the range will be from 0 to 2 pi. So it will be rt 0 to 2 pi. So ultimately my answer will be 2 pi r. Okay, and we all know that the area of the circumference, we have a formula for that, which is 2 pi r, right? So therefore things are matching. Okay. The next topic is speed along a parametric path. So as I said, parametric equation has its physical significance. We can represent the path of a point by using parametric equations to say this particle is starting from there and going till there in certain time, and the equation is given as xt yt like this. Then we can talk about the speed of this particle, right? So the formula for speed here will be just ds over dt. So, we know that ds is the arc length formula is this. So therefore, ds over dt will be just square root of dx over dt square plus dy over dt square. That's it. Okay. Yeah. Up next is surface areas for surfaces of revolution. So recall that what do we mean by revolution? So say this is this red line is equation of a curve, parametric curve. So at t equal to a, the particle is here, and at t equal to b, the particle reaches there. Now, if I say that revolve around x-axis for this curve, then I'll get this sort of surface, right? I guess by now you know what do we mean by revolving. Revolving means we just fix that curve and then try to rotate that 360-degree around this axis. So therefore you will have sort of like a bell-shaped structure or something like that. And this is the picture when we revolve around y-axis. Okay, the same sort of phenomena going on. Recall that the formula for when we revolve around x-axis was 2 pi y ds. And when we revolve around y-axis, we have 2 pi x ds. These are the formulas when we have, equation involving xy only. Now, again, if instead of xy equation, like say x squared plus y squared equal to 1, instead of this type of equation, if I have x equal to ft and y equal to gt, where t is going from a to b, if I have this parametric equation, then also my ds will be just square root of dx over dt square plus dy over dt square gt. And we can use these expressions to get corresponding formulas for surface of revolution for parametric curves, right? So let us focus on examples. So if I look at this example where I have this parametric curve and we are revolving around x-axis, what will be the area obtained by rotating around x-axis? This is the question. So this red line is again representing this parametric curve. Now we are revolving around x-axis, so therefore we'll get this sort of structure. And if I use the formula that I discussed before, this is the formula when we rotate around x-axis, right? So therefore the formula is just integration 2 pi y ds, right? Now ds, as I said, will be square root of dx over dt square plus dy over dt square dt, right? Now do the simple calculations. So x is t to the 4. So dx dt will be just 4 t to the 3 square. And similarly, dy dt will be just 3t square, and dt is as it is. So this will be 16t to the 6 plus 9t to the 4. If I take t to the 4 factored out, then I'll get square root of 16 t square plus 9. And I can take this t to the 4 out of the square root. I'll get t square root of dt is there. 16t square plus 9 dt. Okay, so far so good. Now let us put that expression in our formula. Then I'll get 2 pi. What is y? Y is t to the 3. So t to the 3 will be there, and there will be ds, but ds is this, so therefore I'll get t square square root of 16 t square plus 9 dt. Okay, a little bit scary expression. So this will be 2 pi t to the 5 square root of 16 t square plus 9 dt. And now t is varying from 0 to 1. Okay, so the intuition will be from 0 to 1 as well. Okay, now we have to use substitution. So if I substitute u as 16 t square plus 9, then my du will be just 32 t dt, right? And t to the 5 dt will be u minus 9 over 16. Okay, let me just do it this way. I can write t to the 5 as t to the 4 times t dt. Okay, now t to the 4. So from this line, I can say t square is just 16. No, t square is u minus 9 over 16, right? So t to the 4 will be u minus 9 over 16 square, right? And t dt will be du over 32. Okay, if I just cross multiply this 32, I mean, if I from this line I can say du over 32 is t dt, right? So I have used that there. Okay, now if I put all of this again there, then I'll get 2 pi integration 2 pi over 16 square times 32 u minus 9 square to this u minus 9 square, and then I have u to the half du. Okay, now so 2 pi over 16 square 32 comes out, and I have u minus 9. So this square, I mean, I'll have u square minus 18u plus 81 times u to the half. And this is not hard to handle. You can complete the in-between steps, but at the end, your answer should be something like this. So at the end, your answer should be pi times 6823 over 4480. Okay, a little bit weird looking, but yeah, it is what it is. Okay, one more question that you should think of is, what if we rotate not around exactly x or y axis, rather a axis parallel to x and y? For example, if I have the same question, same parametric curve, and if we rotate around, say, uh, y equal to minus 2 axis. So yeah, so instead of this axis, okay, sorry, just a second. Yeah, instead of this x-axis, if I rotate around y equal to 2 axis, which is parallel to x-axis, then what happens? Then the curve will be a little bit weird, but the expression for that would be just 2 pi y plus 2 ds. Okay. So when we rotate around x-axis, the formula will be this. And when we rotate around y equal to minus 2 axis, then our formula will become this. Okay. And then I can just modify this. I can write the expression for y, which is t3 plus 2, and ds is as same as this, right? There will be no difference in ds, which is this. This ds is same in like it is independent of which axis we are considering. Is it x-axis or y-axis or like x equal to minus 2 axis or whatever. So here also the expression for ds will be t square square root of 16 t square plus 9 dt. And then rest of this will be like similar to the previous problem. You have to do the substitution and then you will be able to figure it out. When I have x equal to minus 2 as the axis on which we have to revolve the curve, then the expression will be just 2 pi, kind of similar, x plus 2 ds, right? Integration. So this will be 2 pi. The expression for like parametric equation for x was t to the 4. So t to the 4 plus 2, and then ds will be t squared 16 t squared plus 9 dt, integration 0 to 1. And the rest again follows just like the previous problem. Okay, so how this x is same as t to the 4? Because this is the parametric formula, remember? X was t to the 4, y was t to the third. Okay. And another question that you might ask is, how do I get this red line as the graph of this parametric equation? Because I changed this parametric equation into this this Cartesian xy equation, and this equation is pretty known because it's like y to the 4 is same as x to the third, and this equation is basically this red curve. Okay, so you should be able to draw this xy equation, but if you are not confident, you can use some graphing calculator like a Desmos or something. Okay, cool. So this is all about calculus of parametric curves. If you have any questions, concern to solve any of the problems of homework 7, you can always mail me. Thank you.